Okay, so we'll be continuing with the current frontiers of quasar and AGN research. Peter Goldreich had a lot more children than his wife knew about. I guess there was Bruce Peterson, who was a student of Maarten Schmidt, and that's not the B. Peterson who's speaking next. That's Brad Peterson at Ohio State. He's been one of the pioneers for many years of the physical measurement of masses of black holes, and he'll tell us about masses of quasars.
Okay, thanks. There was Professor Faulkner this morning mentioned that there was an official vote on the title or the word quasar at the second Texas Symposium. Actually, the result of that vote was published in Nature. Would anyone care to guess what it was? There were 20 ayes and 400 abstentions. All right. So first thing I want to do before I get started is I want to try to draw a distinction between direct methods and indirect methods of measuring black hole masses. The direct methods are ones that are based on the dynamics of gas or stars that are accelerated by the central black hole. So these methods would include stellar dynamics, gas dynamics, and reverberation mapping. Then there are also indirect methods, and these are based on observables that are correlated with the mass of the central black hole. So we usually don't call these measurements, we could usually call them estimates, and they would be things like from the M sigma relationship, or the relationship between black hole mass and bulge luminosity, fundamental plane, or the radius luminosity relationship, which Juna talked about, and I'll have a few words on later. We also distinguish between primary and secondary methods, and this is a little more arbitrary, and it depends on the number of model-dependent assumptions that you have to make. But what I wanted to point out is right now, the reverberation mass scale currently depends on a zero-point calibration that depends on other methods. So therefore, technically, while it's a direct method, it is also a secondary method. It will soon, however, because of direct modeling of the response to the emission lines, achieve status as a primary method. I'm quite sure of this. All right, how do we know the masses of AGN? So if we go back to the very beginning, if we go back to the work of Lyndon Bell, and where he argued that the centers of quasars must be dominated by supermassive black holes. Well, then right away, once we have that, we start thinking about the Eddington limit, and we start coming up with a limit on what the masses of these things must be so that gravity wins over the outward radiation pressure. And what we find for a typical quasar luminosity, this requires a mass that is in excess of 10 million 10 million solar masses. So that's not much to go on, but people have always had a great hope that the emission line spectra would tell us something, because what we have here is we have a nebular spectrum that's characteristic of a 10 to 4 degree gas, but moving it hypersonically. So it was thought at very early times this must be motion within the deep gravitational potential of the central black hole. But that's only part of the equation. That will give you the velocity dispersion of the gas, but the other thing that you need to know is a characteristic size scale. And that was hard to come by. In the 1980s, the way that we came by this was by photoionization equilibrium modeling. And this is basically where Davidson recognized the importance of two parameters that control what a spectrum looks like. The first is the number of ionizing photons that are impinging upon the clouds. And then the second is an ionization parameter, which is the ratio of ionizing photons divided by the cloud density. So this has something to do with ionization rate. This has something to do with the recombination rate. So this is somehow the thermostat that a quasar adjusts to control what the spectrum looks like. So I'm just going to mention it independently, just as an aside here. If you could rearrange this equation here, this is where you get the supposed dependence between the radius of the broadline region and the luminosity of the AGN. And the hidden assumption in here is that the ionization parameter and the cloud and the particle density within the emission line clouds is about the same in all AGNs. That's why I always refer to this as a very naive sort of assumption. So what you find when you do model the broadline region in fairly well-studied objects like NGC 4151, and this goes back to 1982, you find a number of things that are disturbing, that a single cloud model can't simultaneously fit both the low and high ionization lines. You got an energy budget problem, too. There's more energy in the lines than you can produce from the continuum that it sees. And then this, however, is where we get our estimate of the size of the broadline region. And for fairly healthy Seifert galaxies or wimpy quasars, the size of the broadline region then ought to be order of a light year or thereabouts. In particular, the important ratio is the ratio of carbon-3 to carbon-4, which is about 20%, and that tells you then that log U is about 10 to the minus 2. I'm sorry, U is 10 to the minus 2. And the particle density is pretty much set by the fact that this line exists. It's a intercombination line. It has a critical density of about 10 to the 10th, or a little bit less than that. So you have then a handle on those parameters, and you can then estimate what the size of the broadline region ought to be. Well, people started to notice fairly early on that the emission line spectra changed over time. Now, this is, you see that these are rather dramatic changes, and these are the kinds of what we would call these sort of changing type AGNs now. But you can see what photographic spectra look like. They're not very good, and you could only really detect the really largest sorts of changes. Okay, here we go, audience participation. How many people in the audience know how to determine which side of the photographic plate has the emulsion on it when you're in the, how many people? Okay, that gives me an idea of the demographic I'm talking to. Okay, so anyhow, you see some dramatic changes here, but these are changes that are occurring on time scales that aren't tremendously disturbing. But when we started looking at these more closely, we found that they were varying rather rapidly. One of the first monitoring programs was undertaken by Ski Antonucci and Ross Cohen on NGC 4151, and they observed these changes sort of month to month. And this people would have at the time, people said, observing Seyfert galaxies once a month is just, that's crazy town. You don't do that. And I had basically the same sort of experience monitoring Erkelion 120, which in this one is a more luminous AGN. And you can see, again, month-to-month observations show this disturbing thing that the emission lines are varying extremely rapidly relative to this expectation from photoionization equilibrium models. Okay, so ultimately, this has led to high sampling rate reverberation mapping, where we look at how the continuum varies with time, and we see that the emission lines follow. They show the same pattern of behavior, but with a slight shift, and that we interpret that shift then as being the light travel time across the broadline region. In this particular case, we see that it's 14 days, and this is sort of an intermediate luminosity Seyfert galaxy. Now, just to give you some intuition for how the lines ought to respond, we're just going to walk through a short tutorial here on reverberation mapping, because, of course, we're going to imagine that we have clouds that are in circular Keplerian orbits around the black hole at the center. The observer is off at an infinite distance to the left here. Now, this is not what we can observe, because the projected size of the broadline region is still, it's 100 microarcseconds or something in the nearest bright AGN. So this is spatially unresolved. But what we will do is we're going to map this now into two observables that we have. One is the time delay, a time delay between a continuum event and the emission line response, and then the other one being the Doppler shift within the line. So we have two physical parameters then that we can measure, the time delay and line of sight velocity. So if we look at a circular orbit and see how that projects into this velocity time delay space, well, we see that, of course, a point that's right along the line of sight, assuming that it responds instantaneously to a change in the continuum brightness, will respond immediately with no time delay as the continuum photons and the line photons head off from this place with no delay between them. That projects then right down here to a Doppler shift of 0 and a time delay of 0. And if we look at other points along this path, what we will see is they go to progressively longer and longer time delays till we get to the very far side, which then is going to be 2R over C. Because basically what happens is it's a continuum event here. Part of the continuum goes off here, gets reprocessed by an emission line cloud here. Part of the emission comes back in this direction, and it's traveled 2R over C just to catch up with continuum photons that are headed in this direction. So the important thing that we see here is that a ring projects to an ellipse in velocity time delay space. Okay, so again, just a little tutorial. It just shows you how this works. Again, emphasizing the fact that we have the circular orbit projecting to an ellipse in velocity time delay space. Okay, so we can go to multiple ring systems. We have two ring systems here, an inner one and a larger one. And the The inner ring then is going to have larger velocities and smaller time delays, and it's going to project then also to an ellipse, but we see that it's small compared to. So it's trivial now to go to a disk, because we can look at a disk as just a construction of a large number of rings. So what we see is the response of this emission line then. Initially, we see that there's quite a rapid response over a broad range of velocities, and then this tapers with time as we look at the far side of the region, which is then dominated by motions which are primarily transverse. Okay, so just a little movie on how this is going to work. Now, if we set off a flash bulb, an ionizing photon flash bulb at the center of the AGN, and we watch all the continuum photons propagate out to this, we will see that about 10% of them then get intercepted by broadline clouds, are instantaneously reprocessed into emission lines, and then we can assume that these are emitted isotropically or however you would like. And some of them then head off in the direction of the observer. Now, at any given time then, the locus of points that the observer sees responding are located along a surface of constant time delay. Now, this is a frame from a movie that I'm going to show you, a particular frame that's taken 18.6 days after this continuum event. And what we see is, at this particular time, is all of the points that are responding are along this single isodelay surface here. Now, if we go into our observable space, which is velocity and time delay, of course, the surface of constant time delay becomes a line. And what we see down here in this panel here is the instantaneous profile that you see in response to the continuum outburst. So this is basically what we're looking at. It's a system of nested paraboloids propagating through the region, and we see the emission line response as a function of time. And I'll just run that by one more because it took a lot of work to do this, and it's kind of cool. So this is the way an AGN would respond to a delta function outburst. And unfortunately, nature doesn't give us delta function outbursts. So what we have to look at is a convolution of this response, which we call a velocity delay map, with the continuum history. So you can see from inspection that if we replace this with a delta function, what we see is that what the velocity delay map is actually then the velocity result emission line light curve. What the light curve is the, I'm saying this all right, I'm sorry. The velocity delay map is the emission line light curve that you would see in response to a delta function outburst. Okay, so what we have to do is we have to try to disentangle this, and this is what a real velocity time delay map will look like. And this is a beautiful velocity time delay map. This was obtained by the LAMP consortium on ARP 151. So the problem with this is that this is really resource intensive. You have to have high time rate sampling, you have to have sufficiently long duration, and you need very high signal to noise. So this is not one of these things that's trivial. Over a reverberation timescale, an AGN typically will vary by 10 or 20%. So you have to have excellent flux calibration all through your monitoring campaign. Okay, here are some recovered velocity delay maps. It's only within the last few years that we have had data of sufficient quality where we could start to reconstruct these from the data. You can see that, for example, 3C120 here sees something that looks maybe like a disk. We see a couple of things here, like this one in particular and this one, that look as though these are infall. These are infall signatures, because what we're seeing here is the red side of the emission line responds first. So this is the part, this is the gas that's moving away from us, but is preferentially on the near side. Every one of these shows the same signature, that the red side varies before the blue side. These are all these are all lines that we see in the optical combinations of the Balmer lines and helium-2 4686. Okay, so we can also, this is also a very simple thing to do because the response is a linear response, or can be linearized because the variations are so small. So if you have many things going on, you can actually just add these up. So you may have several different components that it takes to explain a fairly complicated velocity delay map, as you see here. Okay, now that's cool and tells us something about the broadline region structure, and we hope that with modeling we will be able to get accurate masses out of that, and there are people who are doing that now. But we can still get useful information out of this just by simply cross-correlating the continuum and emission line light curves. And we then get a typical size of the region. This is sort of the average light travel time across the region. And this turns out to be extraordinarily useful because this is that size number that we needed to combine with the line width to get the mass. So we're not learning much about the structure of the broadline region here. We're just learning its typical size scale. All right, this is one of the best multi-wavelength data sets that we have, which I find tremendously embarrassing because this is 25 years old. If we look at the ultraviolet continuum, as you see here, we see a number of events over this 240-day program. Here's the optical continuum at the same time. And then we go through these emission lines, helium-2, 1640, Lyman alpha, carbon-4, carbon-3, and H-beta. And in this panel here, we have taken each of these light curves and cross-correlated it with the ultraviolet. And what we see is that the lines that are characteristic of lower ionization media take longer to respond than those of high ionization media. So we've clearly seen then evidence of ionization stratification. The highly ionized stuff is closest in. Now, the other thing that we have to do is measure the line widths. The way that we generally prefer to do this with the reverberation data is, well, we take all of our spectrum, we add them together, and we can make a mean spectrum. But we can also then isolate the variable part of this spectrum by computing the root mean squared residual spectrum. That just isolates the part that varies. So you can see the difference between, say, a mean spectrum and an RMS spectrum here. Okay, and here, for example, we looked at this one already, Markarian 335, and you see, it's interesting that you see how well the helium-2 4686 line stands out in these RMS spectra compared to the mean spectra. Okay, now, when you do this for multiple lines in the same object, you find this really critical result, namely that there is an anti-correlation between the line width and the lag, and it actually is perfectly consistent with the line width going like the inverse square root of the size of the region. And this is exactly what you would expect if gravity is dominating. Now, remember, we haven't yet identified whether or not radiation pressure is important to this, but radiation pressure, of course, is also a 1 over r squared force. So if there's radiation pressure working as well, it makes it look like there's less gravity. So we're underestimating the masses of the black holes if there is radiation pressure, and we haven't taken account of it. But okay, so in every case that we've been able to measure multiple emission lines in particular AGN, even at very different times, very different epochs, what we find is consistency with this. And this indicates then that we may be okay using this to measure masses. So the way that we measure masses, and this has actually been covered, Lewis mentioned this as well. Let's start out with the observables. We have two observables. We have the emission line width, and there's lots of, there's a number of different dogmas on how to measure that. Then there's the size of the region that you get from reverberation. Divide this by g, and this gives us then an observable that is in units of mass, and we just call it usually the virial product. Now, we need to put this, though, on a mass scale, because the thing that's missing here is we haven't made any correction for the geometry of the broadline region, or the fact that we're not looking at it edge on, probably. We're probably, in fact, more likely to be looking at it face on. So what we want to do is, in the absence of any additional information, what we're going to do is we're just going to multiply this by some fudge factor, which is set by where we just subsume everything that we don't know and put it in that. And if we have some other way of measuring the mass, we can determine what this factor f is. Or if we at least have some statistical way of doing it, we can determine what an average value of this is. And then what we have done to do that, to measure that, is to use the m-sigma relationship. What we have done is if you plot the AGN m-sigma relationship and the quiescent galaxy m-sigma relationship on the same graph, what you'll see, the AGNs, which are blue and green here, will actually be down below it. But if we assume that they're really intrinsically the same and shift them up so they match, then we get an average value for this f factor. And this works out to be about a factor of around 4, somewhere between 4 and 5. This seems large when you first look at it, but what you have to keep in mind is when you're looking at type 1 AGNs, you are looking preferentially at rather low inclination angles. You're looking at them nearly face on, so the projection corrections can be potentially quite large. So I'm not particularly disturbed by that number. Now, the other thing that you can do is you can look at the intrinsic scatter in this relationship, which works out to be about 0.4 dex. And that tells us then about how accurately this is working, just using this mean, this mean f value that you see here. We can also check this. Now, this one is a better check than you would think, because this line looks like it is a fit to these data points. It is not. The data points are all measured. This is a relationship between black hole mass and bulge luminosity. All right, so the bulge luminosities were all obtained with Hubble Space Telescope images that we deconvolved and took off the central point source. So it's just the stars, not the AGN. And the black hole masses are the virial products that we obtained from the reverberation program, and then all multiplied by that scaling factor, the average scaling factor. The straight line that you see here is actually a fit to this relationship for quiescent galaxies. So this is actually a nice confirmation that of the validity of the reverberation-based masses. And we also, in a handful of cases, you can resolve or nearly resolve the black hole radius of influence for nearby AGNs, and you can make a direct measurement using stellar dynamics or gas dynamics. And what you see is that given that there's sort of a factor of 3 uncertainty, they're generally in pretty good agreement. If we look at NGC 4151 here, I mean, this one's just, yeah, this one's like silly, that how well this and this agree. But remember that they are probably both uncertain by at least a factor of 2. But, you know, it's nevertheless, it's encouraging somehow. We seem to be on the right track. Okay, now the reason I've been emphasizing reverberation is, of course, this is what you use in quasars and type 1 Seyfert galaxies, and that's really kind of in the spirit of this meeting. And the other thing is that this is the way in the future that you can make direct mass measurements. What we see here is the green lines here indicate where the radius of influence is resolved for black hole masses given along this axis, along distances given along this axis. So what you see is that with HST at the calcium triplet, for example, you can only resolve sources above this line. For the 8 meter at H-band, it's this dotted line, and even with the 30 meter at H-band, it's down this line. So what you see is that reverberation is not constrained by angular resolution. What you're doing is you're substituting time resolution for angular resolution. So if you want to get out to large distances in the universe, reverberation mapping is clearly the way that you're going to have to do it. And the downside for this is that it's resource intensive. It takes many observations to get a mass. And that's why, so if you want to significantly increase the number of measured masses, you need to go to secondary methods. And these have been talked about already, so I'm just going to mention very briefly this relationship between the broadline region radius and the AGN luminosity. I love this series of photographs here because we're going a factor of 10 farther out in each case for AGNs that have the same apparent brightness. So each step out is a factor of 100 in luminosity. Now, the reason I put this up here is to emphasize that we use fairly large spectrograph slits to mitigate against seeing effects, et cetera, to get an accurate flux calibration. When we do these reverberation measurements, that lets in a lot of starlight. So it's critical that you somehow correct for the starlight when you're looking at this radius luminosity relationship. And we have done this here. Here is the most recent version of the radius luminosity relationship. It has a slope that is pretty close to the expected value of 1/2. And we see that the amount of scatter in this is very small. The intrinsic scatter is about 0.13 dex. And the typical error bars on the best reverberation data sets are 0.09 dex. So you can do almost as well with this radius luminosity relationship as you can with reverberation, again, provided that you can account for the host galaxy flux fairly accurately. Now, this has also been independently confirmed by gravitational microlensing observations, which have shown that there is also a radius luminosity relationship seen there. The red points are the microlensing of the low ionization lines. These 2 points are a little to the right of where they should be because the host galaxy hasn't been taken out. If we look at the high ionization lines, what you can see is, again, there is a parallel track here, perfectly consistent with the fact that there is also a radius luminosity relationship in carbon-4, but carbon-4 is closer to the central source than H-beta. Okay, something else that I wanted to mention. Okay, I showed you this diagram before. 29 years ago, I went to one of my first international AGN conferences here in California, and I showed these data, and I said, guys, the broadline region is like 10 times smaller than what the theorists are telling us. Well, this was not met with universal acclaim. I mean, you know, people People questioned my sanity, my competence, whether my parents were married when I was born, all kinds of things like that. So then another really obnoxious trait of people my age is that they like to revisit their youth. So in the spirit of doing that, I'm going to come and make another outrageous claim. My new outrageous claim is that the narrow emission lines vary in at least some of these sources in NGC 5548. So what I've done is this is observations over many, many campaigns by the AGN Watch, by my group, by LAMP, my group again. And what we have seen, if we look at the spectra that were attained under photometric conditions, what we see is that the O3 flux gradually decreases with time. Now, this means a number of different things to a number of different people. If you're interested in the narrow line region, you can actually use this to measure the size. Now, we don't do real reverberation as such because you've got two delay time scales now in this lower density gas. You have the light travel time, but you also have the recombination time. So it's some combination of this that smooths the spectrum of the O3 emission. So if we actually make this diagram here where the observations of what T-smooth has to be is shown as a function of the radius of the narrow line region and the electron density, it follows this curve here, which has some pretty large error bars on it because we don't have a lot of data on narrow line region timescales. But we also have some physics that helps us out here. We know that we've got to be above this line here because this is for a filling factor of 1. We just given density, there's just so much gas you need to get the total emission that you measure. And then we also have the critical density for the O3 lines right in here. So it's somewhere in this wedge bounded by these dotted lines. But what we see is this is somewhere, then this gives us a size that's somewhere between 1 and 3 parsecs and gives us an electron density that's around 10 to the 5th or thereabouts. So now the reason that this is of interest to me is because we use those narrow lines to do the flux calibration of our spectra. We need a relative flux calibration that goes night to night that has to be accurate at sort of the 1 to 2% level. And it's very hard to do spectrophotometry ground-based and get accuracy more than, I don't know, 4 or 5%, something like that. So this means that over history, then, we have to correct these previous campaigns for the fact that the narrow line flux has actually decreased over time, meaning that the fluxes from the broad line region, from the continuum source, have actually gotten fainter than we thought. So this is the red symbols that you see here are the uncorrected light curves, and I've overplotted in black the corrections. So the corrections are quite small, and on short time scales, they're just negligible. So this does not affect any reverberation results that have been published to date. Okay, so to conclude, reverberation mapping has now reached a level of maturity where we can trust the masses somewhere at around 0.3, 0.4 dex. Excuse me. And this is actually pretty good resolution. People say, well, why can't you do it to 10%? Well, okay, we're working on it. But, you know, to get it to a factor of 2 or 3 when we're looking at masses that span more than 3 orders of magnitude, that's not so bad. We're also then, because we're able to recover some velocity delay maps, we're starting to see some of the structure and kinematics of the broadline region as well. And then notably lacking are any recent observations that include the ultraviolet. Well, we're about to fix that because we were just granted 180 orbits of HST time to monitor NGC 5548 for the purpose of reverberation mapping. So this is something that's we're going to start probably towards the end of January is where it's on the schedule now, and it will be 1 observation per day for 6 months. So the basic goal that we're looking at is we want to get the first high-fidelity UV velocity delay maps, for the reason that we don't expect that the gas emitting the UV lines is doing the same thing that the Balmer lines are doing. They probably come from very different regions. We've known that for a long time. Remember the photoionization modeling that I talked about in about the first or second slide. The other thing that's happening is that people are working on techniques where you can do reverberation mapping on industrial sort of scales, where you can get more than, you know, half a dozen objects per campaign. Again, these are techniques that are under development, and they have lots of potential applications, including getting masses to very large distances, and potentially with cosmological applications as well. Because if you can measure the radius You can infer the luminosity. You compare it to the flux. You get the luminosity distance. Okay, so I will stop there. Thank you very much. Yeah. Okay, we don't have velocity delay maps for those yet, and we're still working on those. But if you just look at the gross kinematics, compare the blue side, the red side. Yeah, one of them looks like it's an outflow, and one of them looks like it must be just circular orbits or something. So we're still working on that, but there are problems with that data set that have not allowed us to extract the velocity delay maps yet. But yes, good point. Keep me honest. Okay. Oh, when you're looking face on, you know, yes. You use what happens if you have just a ring is what you'll see is everything responds at the same time delay and at all velocities, which is at face on is 0.
So how well can you then determine the inclination from a measure?
We don't know yet, and it's because this is the first handful of velocity delay maps that we have obtained. So yeah, that's one of the things that we want to be able to do is to determine what is the inclination of the region.
Yep.
So Brad, you alluded to a variety of results from the delay maps. Implicitly, you talked about the measurement suggests flat disk, but you also mentioned inflow, Eric mentioned outflow. Is there a consensus? How does the picture look right now?
The picture right now is that all of the velocity delay maps, and Aaron, you can correct me if I'm wrong, all the velocity delay maps that I know of have an infall component. Some of them look like they may have a disk component. Some of them look like they are just spherical infall. So what we're seeing is a wide variety of situations so far.
Yeah.
The spectre of 4.9 or whatever, F,
Mm-hmm.
which seemed, the way you were presenting it sounded like you were saying disks seem more face on. It could also be in a sphere that is more projected area, of course, tangential to the sphere. What constraints do you have on the thickness of that disk distribution?
Not much. I don't think that the velocity delay maps give us some constraints on, say, inner radius to outer radius and on inclination. But I don't
mean width, thickness. I mean the thickness along the scale height of the disk.
Scale height of the disk. Okay. Right. Yeah. Right now, I don't think that we have any constraints, but I probably haven't thought about that hard enough.
Okay. I think we should move on to the next figure. Thanks,
Okay.